right now. And second, I would like to show you that GPU computing actually match very well database, and that database using GPU computing as a power engine basically provide amazing results, and they are really, really fast. Okay, so you ready? All right. So who knows NVIDIA here? All right, yay. Who knows NVIDIA outside of gaming? Yeah, there are still some. Great. Yes, NVIDIA is known. All right, okay. That's fine, no problem. So yes, NVIDIA is well known about gaming. Okay, we created this GPU in 1993, I think, yes. And this GPU was created for gaming, for graphic rendering. You know, we created this massively parallel architecture with a lot of core to work on the shaders and work on graphic rendering, being able to push a new image every 60 frames per second and 90 frames per second and now 120 frames per second. That was the base of GPU computing. And that was not all that. 12 years ago, our CEO decided to open the programming language of the GPU. It's called CUDA. Okay? So CUDA is the programming language of the GPU, and he wanted this programming language to be available everywhere, on every platform. So all our gaming platforms were able to be transformed into a computing platform via this CUDA language. And a lot of students, a lot of people started to play with that because it's so easy. I mean, you like gaming, you game, suddenly you stop, and you can do some type of homework or research and building some algorithm with CUDA. That's the base of GPU computing. And I will describe that a little bit better because it's a little bit more complex than that. But that's the basis. And of course, computer graphics was the base of our activities for a long time. And it's still there. And gaming is a huge part of our business. And it's still growing business. But it's not only that. We're using computer graphics to simulate the world, basically. And simulation is a very important aspect for HPC. So we are doing simulations for pharmaceutical industry, simulating the drug interactions, or our drug combined to a virus and basically converge. We are simulating for oil and gas industry seismic simulation, in order for those guys to understand where is the next pouch of oil and where to drill correctly. But this is also used to simulate the world that will happen. So today I think that every car in the world are using NVIDIA GPU graphics to design the cars. So the design, I would say, industry is using GPU a lot. And next, we realized that this parallel architecture of the GPU was really great at crunching number, which is the base of the simulation. And one of the most intensive crunching number application right now is deep learning. Okay? And we put a lot of resources in building the libraries using CUDA that will take advantage of the GPU and make GPU platform the best platform for deep learning. And today we are the leader in deep learning. All the big companies involved seriously with deep learning, like the Google, the Facebook, the Amazon, Azure now, Microsoft is very involved, and Baidu, and others are all using GPU for that. So threefold: GPU computing, computer graphic, and artificial intelligence. So, I think it's yes, it is. How GPU acceleration works. So basically, when you build an application code, you have pieces of code that are sequential, and other pieces of code where really the heart of the application, the crunching numbers, the parallelization part resides. And that's the part you want to offload to the GPU. So GPU computing consists of a CPU for all the sequential and the GPU for acceleration. So it's basically, for all the gamers, it's basically the same architecture of a gaming rig, but you translate this architecture into a server architecture. And then you put that and write that in your data set. Okay? So even if the part of the code that is very intensive and compute intensive could be only 5% of the line of the code. It's the one that requires the most power, or where the application will spend most of the time. This is what you want to avoid. Because you can see briefly represented here that the CPU is probably a few core, up to 10, 24, 32 now, really big CPU you can find on servers. GPUs and the latest P100 architecture is 1200 cores. Okay, so it's completely different. It's another word. And the memory and all these things is architecture. So of course, the cores are less complex. They are faster. They may be simpler, but they do great things at every mathematical operation. So, and just to show you an example about the differences, it's here. So here you have different metrics over here about first the power, it drops. Okay, multiple operation per second you can have. And you have two trends here. From 2008 to 2016, you have the evolution of the x86 CPU, basically reaching a little bit more than a gigahertz. And here's the evolution of the GPUs. Okay? So from K20, K80, which are Kepler architecture, up to Pascal, our latest generation of GPUs, it's greater than 5 gigahertz. I mean, this is just this gives you a little bit an idea about where we are going when we say we really want to have a massive parallel throughput engine as a GPU. And the second graph on your left-hand side, your right-hand side, sorry, missing you. On your right-hand side is the peak memory bandwidth, because it's great to have a good engine, but then you need to fuel that engine with a lot of data. And so we work a lot about how to push data into those GPUs. And right now, our latest Pascal GPUs with the latest HBM2 memory that are co-packaged on top of the GPU on our latest P100, whether they are PCIe or SXM2 form factor, those memory bandwidth is 732 gigabytes per second. I mean, that's really, really fast. But that's what you want if you want to crunch a lot of data and converge faster. All right, so the results in terms of the data center. When you use basically the old or traditional CPU architecture, this is what you have when you need to scale. Because we all know that there is a deluge of data, that the data are arriving and growing exponentially. Everybody wants to gather data, everybody wants to have more and more data, everybody wants to get the insight of the data, and so they gather data. And to answer those requests from the data scientists, most of the time, a lot of companies need to scale and put more and more servers into the data centers. The issue here is that you start to add a lot of interconnects onto that, okay? And the end result is that it costs a lot of money, it costs a lot of money to cool down, it costs a lot of money in real estate, it costs a lot of money in network fabric, and at the end, your data center cannot scale linearly. Okay, you have a loss of efficiency. It's not because you double the size of your data center that you will double the efficiency of your data center. Okay, it doesn't work that way. So our answer is to put way more power in the server. You put GPU into the servers, you can put 1 GPU, 2 GPUs, up to 8 GPUs in the largest one, and then the power of your own server is multiplied by 10, 20, even sometimes 50. Okay, and then you can do way more things and you reduce the footprint of your data center. That's what we call strong scale. Alright? Alright, so everybody has his own little slide to explain that data is exploding, that's the deluge of data. From the business process up to the AI world, we live in the AI world. There's definitely a lot of different applications that either generate or need data. And it's really growing. So I would like to pause here just for a second and ask you a quick thought. What is the size of the database you are working on? So there are probably a lot of students still here, maybe people that are starting to work with database. Do you have database larger than, I don't know, 100 gigabytes? Yes? 1, 2, 3. Okay. 500 gigabytes. You can keep the hand, your head. Okay? 1 petabyte. Yeah? There's still one? Only one? 5 petabyte? Okay. So when you start to reach this petabyte phase, you need a very powerful machine. Or you need to do things a little bit less, how can I say? You need to do less things, let's say. Okay? Today, data analytics are used by a lot of different applications. I mean, from automotive, communication, consumer packaged goods, financial services, retail, oil and gas, all those companies are using data analytics. There are so many use cases. They all want to improve their process, okay? Or they all want to better serve their customers and increase their bottom line. That's the purpose. And they think that within the data they are generating every day, every minute, every hours, every second in their process, they want to see the truth, see patterns, and find ways to get better. So, this is one of the situation I'm seeing a lot of times. So part of my job is to go to enterprise and to understand if they know GPU computing, and to tell them we can do great things with GPU computing. Okay, we can accelerate your database drastically, we can do deep learning, and there's a lot of things we can do to help you in that. And most of the time I see 3 different types of people. I see on your left-hand side the business case owners. Most of the time they are the C-level or they are business-oriented person. They say, we want to do that. I heard that we could streamline our process and our supply chain and save a lot of money onto that. We can do ad tech. Ad tech is something new. I can push very dedicated ads to focus customer at the right time, at the right moment to increase my conversion. Okay? And they are talking to each other, and they know things are happening. And so what they say, they ask the data scientist to execute. And the data scientist is in the middle here, and he's like, my tools are not fast enough. I would like to have more power, more tools. I would like to have tools that are open source API that can deploy faster, and my performance is not fast enough. And they're going to release this flow of IoT device in 2 months, and it's going to be even worse. So that's really the struggle. I mean, that's why you're here. You're here to study the new techniques and make sure that when this guy on the left-hand side will ask you, hey, I need to do that, you can say, yes, I can, or I need to have this with me in order to do it. And what you need in terms of computing power to really achieve that, it's reside within the hands of the IT engineers. So they are the ones that have the computing power. Okay? Most of the time they are the ones that have the checkbook as well. They will want that will pay for that. And those guys, they are like, GPU computing, what is? Why do I need that? I always work with this, and it's enough. I mean, if you want more power, I need to double the size or triple the size. Oh, it's expensive, and I don't have the room for that, and I don't want to pay for that. And what you want another thing is going to be another one-trick pony, you know, that will be like an exotic solution to address exactly your use case, but nobody else will use it at the company. So those are the discussions I have with most of my customers trying to convince the IT guys. Because GPU computing, due to this programmability of it, you can run accelerated database onto it. But you can run deep learning, you can run HPC, you can run a wide variety of applications. We are seeing also data scientists using accelerated library in R, in Python, some specific algorithm, and they are deploying those specific libraries using the CUDA to make them run way faster on GPUs. All right. So what happens when your system is too slow? If you have long response time, basically you will ask questions, you will most likely know the answer. you won't go into the details. That will limit your creativity. You will not spend the time to really explore and dig further because your system is too slow. Because when you send a query, you will have time to take a coffee or two, or maybe lunchtime, or maybe come back to your place and go back the other day to see the answers. And the workarounds, I would say, they are not the answers. I mean, downsampling, it's not an issue. I mean, I think everybody has in mind the result of the last presidential election, where the polls were saying something and the result was completely different. I mean, polls are really a use case of sampling. They downsamples the category of people, and at the end, if you one category of people, it's only one guy or two guys. I mean, you cannot base a real model out of that. That's not possible. So you need a large number of data in order to build an accurate model. All right, so this is where NVIDIA arrived. So three main axes here: analyze, visualize, and AI accelerate. On the same platform, you can use today databases that take advantage of GPU computing to accelerate. The result of some case is 10 to 100x faster. I mean, that's really, really faster. That's a new computing power, a new capability that opens new use case. If you decide to go into that direction, you will see that suddenly things that were not possible before because you didn't have the compute power suddenly are there. They are possible. So you could do new use case, you can do real-time use case. There's a lot, I think, that was brought this morning, talking about fast data, how fast data are valuable. Yes, you have a lot of data incoming, but you want quick turnaround to understand what's going on and what are the action I need to take depending on this incoming flow of data. If your system is too slow, you're losing value here. Visualization is the DNA of NVIDIA, for sure. And new technology like graph database, it's a great way to represent connection between data. It's used by cybersecurity. It's a great use of data and to measure the connection between different group of users and connection that appears and disappears after time. It's great and it's really powerful. And the third aspect is AI accelerator, because AI, especially deep learning, is based on a big pile of data. And you need to have a lot of data to train your model and to be a good model. If you want to have object recognition, for example, you need a lot of different pictures of a cat or dogs in order for the system to accurately recognize a dog and a cat and make the differences. If you need to build a self-driving cars, you need hours and hours of example of driving in order for the system to recognize the lane, to recognize the other cars, to recognize the signs, and to interpret them. So, because the data are exploding, you need fast tools to analyze it, you need fast tools to visualize it, and the logical evolution of that is to reuse the amount of data to create models using deep learning. And GPU computing addresses all of that. All right, so just an overview about different architecture. So on the left-hand side, you have basically something traditional in the data center, a bunch of servers that come from HP, IBM, Cray, Cisco, Dell, some core technology scheduler like Spark, Hadoop. I'm not talking about the storage here. And then database like Oracle, Cassandra, SAP, Hadoop, and visualization tools like Tableau. If you move of your thinking to translate to the GPU computing words, at the bottom layer you have GPU accelerated data centers. So Tesla is our line of products that are those GPUs. They are PCI form factor or SXM2 on the picture here. And those basically GPU goes into servers, and HP, Dell, IBM, Lenovo, they all deliver great servers that are GPU based. We even created our own, it's called NVIDIA DGX1. It's a beast. It's enormous. We have 8 of the most powerful P100, like this one on this picture. They are connected with a dedicated bus called NVLink. It's a bus NVIDIA created because PCIe was not fast enough. We needed something faster. So it's 5 times faster than PCIe in order to have a great interconnect and all those GPU acting as a massive single GPU. This box delivers 170 teraflops, okay, for FP16, single procedure. That's insane. That's insane for everybody involved into deep learning. They want to play with that. I say, give me one, please, we do. And the other part where you can find GPU computing and access it is in the cloud. All the major cloud providers right now, Azure, Google Cloud Platform, AWS, IBM Softlayer, Alibaba in Asia, they all have GPU computing instance. And it's growing very fast. Even is growing very fast. Some core technology like Big Mac, Spark Mesos used as a scheduler are compatible. Some accelerated database, Kinetica, Stream Technology, MapD, BlazingDB, based in Austin. And some visualization layer like MapD. MapD reuse part of the GPU to do the computation and part of the GPU to do the visualizations. Pretty smart actually. BlazeGraph and Graph History are using Graph. And they are great. They are used by Department of Defense and cybersecurity in most of the case. And on top, the deep learning frameworks. So all those frameworks, 100% of the deep learning frameworks are GPU accelerated. So we have created our own library like cuDNN, cuBLAST, Nickel, that are libraries that we deliver to those guys, and we work together with those framework providers in order to integrate what they are doing to our libraries to create the best efficiency as possible. And so today, when you're running one of these frameworks, if the system detects there's a GPU or not, use all the GPU compatible library. All right, acceleration. So there are a bunch of numbers on this slide. I left it here. It's order of magnitude faster for those different applications, but I prefer this one that gives way more details about where we are going. So basically, every time it's really short, it's time of the query. For MapD, let's say this example here. MapD, it's in-memory GPU accelerated database, and you can compare those queries compared to the other query on other solutions. I mean, the order of magnitude is just unreal. Okay? Kinetica, 50 times faster than leading in-memory database. On other NoSQL database, it goes up to 100% faster. Those are things that's very an amazing shift. People have sometimes issue to believe it, and in some case, on some company that adopted that, the people that didn't see that coming were in trouble. It's that radical that creates this kind of shift and changes. So you can today use those things if you want to start a POC for example. Very easy. There's a couple of, I think Azure, AWS, they have some instance and the application is ready to run. There is a CSP provider based in Dallas called Nimbix. They are specialized in accelerated computing. They have those things already ready on some GPU-based server ready to go. It's very easy. You just have to send your data over there, press a button. The connection is very easy, and you have a few minutes later you're connected to the system and you can evaluate the power of it. All right, BlazeGraph. That's the graph, and here they compare to. So there, many edges do they have? I think it's close to the 2 billion edges configuration, and this is the throughput, or let's say the acceleration you may have compared to a CPU only. And these was run on 2 of them were run on AWS instance. This is the analysis that Scream did with Orange in Europe to replace basically one 2U dev server with Tesla K40. It's pretty old technology. I don't know if you remember the graph, but it's probably 3-4 years old. With a full rack 42U of Teradyne. So an amazing power. And that basically will end my presentation. So basically, just a few things to remember. Tesla is the name of our accelerator that goes into the data centers. Thank you very much. And DGX1 is the name of our AI supercomputer specialized for deep learning. It comes with a fully integrated stack delivered with NV Docker containers. So basically, what we wanted to do here is really to enable scientists and deep learners with ready-to-use boxes. We don't want our user to spend time on toolings and piping and configuring everything and be tool expert. We really want them to focus on the next big experience, on the next big use case they're gonna deliver and release. And GPU computing is available everywhere on the cloud. So you can get it from your preferred server manufacturer, you can access it from the cloud. We even deliver to universities with special programs as well. All right. That was all.
Any questions? We can take 2 questions.
Just a quick question about your Drive PX2. Do you think there's sufficient power already to get to autonomous cars and those kind of systems you already have?
So there are several platforms of Drive PX2. You see the first one we announced last year at CES. The one with Parker. The one we announced this year with Xavier basically will give you to a level 4. Yeah, definitely.
Where do you get that?
One in the back there.
Okay. What's the typical days for GPU to replace?
Okay. So the question was, what was the difficulty or the challenges for GPU to replace the CPU? So GPU does not replace CPU. They are an accelerator, so they are a companion. With GPU computing, you create a new type of server. You know, it's like you have all the components that you need to do the things with a CPU, but it's not. It doesn't go fast enough. It doesn't deliver the value. Okay? So with GPU, you go a step further. So a GPU will never replace the CPU. We still need the scheduling, the booting things of the CPU. It's like a gaming ring. If you want to play, you can play whatever game you like with integrated graphics, but the experience won't be there. I mean, it will be very limited. Some very basic game could be good, but if you want to read something intensive, you won't have the experience. You need an external accelerator with the GPU connected to that. So that's the same thing. Today, what could slow down the GPU computing application is, was the lack of awareness and the lack of ecosystem, or the lack of applications. But right now, it's really growing up to the roof. The number of CUDA developers is now 400,000. Okay, the number of GPU accelerated application for the HPC world moved from 300 last year to 400. I mean, there's definitely a great trend. And it's starting to be, I would say, accepted, deployed, and adopted by the enterprise community at a very fast rate. And the announcements are coming, and when you have 2 or 3 big guys saying, I'm using that, believe me, behind that, a lot of people are moving to that.
All right. Thank you, Alex.
Thank you, my pleasure.